In the previous lecture, we saw that quantum computing can speed up significantly several algorithms from different application domains. Among those applications, for instance, in cryptography, Shor's algorithm can accelerate prime number factoring. In chemistry, we can speed up molecule simulation. We can use the Grover algorithm for fast data search. And we can also accelerate pattern matching in genomics. We saw also how quantum algorithms can be expressed in a high-level programming language such as the OpenQL language designed at QTech. In particular, we saw that those algorithms are composed of a mix of classical and quantum operations. The classical part can be executed on a traditional processor, and the quantum part can be executed on the quantum processor. For instance, the Shor's algorithm is a famous quantum cryptography application for prime number factoring. This algorithm includes classical computations such as the greatest common divisor computation, which can be executed efficiently in a traditional processor, and the quantum part such as the quantum Fourier transform, or the QFT, which should be executed on a quantum processor and operate on the qubits. As we saw in the compiler lecture, the initial human-readable program implementing the algorithm goes through different compilation steps which produce a binary code. That binary code can be decoded and executed by our quantum computer. The goal of the microarchitecture is to execute that code in a deterministic way and provide all the runtime support required to execute both the quantum operations and the classical operation, and then return back the computation results or the measurements. When loading the executable in our microarchitecture, it is important to distinguish the classical and quantum operation. For that, an arbiter unit is responsible of sorting those instructions to distinguish the classical and the quantum instructions and route them to the appropriate pipeline. So the classical instructions to the classical pipeline and the quantum instructions to the quantum pipeline. Those instructions are then decoded and executed either on the host processor or on the quantum processor. One of the main tasks of the microarchitecture, or more specifically the quantum pipeline, is to translate the quantum instructions into analog signals which can be sent or applied to the qubits. These signals can be microwave pulses or constant voltage levels. So each quantum instruction is fetched from the instruction cache, decoded, pushed into the execution queue, and translated to an analog signal using a digital to analog converter. The digital quantum instruction need to be translated into microcode instructions and ultimately translated in the right analog microwave.